Welcome to your AP Statistics lesson on Chapter 26, Part 1. We're going to be comparing counts, and today we're going to be comparing the counts that we observed to a particular model. We are going to look at the chi-square goodness of fit test. Goodness of fit is a test of whether the distribution of counts in one categorical variable matches the distribution predicted by a model. Okay, so there's some model out there, and we want to know whether or not our data that we actually see, if we summarize our data into counts and look at that distribution, if that provides evidence against the model. As usual, there's assumptions and conditions that we need to consider. One is the counted data condition. You need to check that the data summaries or counts for the categories of a categorical variable. So you want to check that the data is summarized by counts and that those counts are actually the categories of a categorical variable. The second thing you want to do is check the randomization condition as for support for the independence assumption. The assumption is the counts in the cells should be independent of each other. The condition we can check is that the individuals who have been counted and whose counts are available for analysis should be a random sample from some population. There's a sample size assumption that we must have enough data for the methods to work, and the way we check that is with the expected cell frequency condition. Now, this isn't what you observe, it's what we're actually going to calculate. We should expect to see at least 5 individuals in each cell. This is similar to the condition that NP and NQ be at least 10 when we tested proportions, but this time the magic number is 5, and that again is for our expected cells. Alright, since we want to examine how well the observed data reflect what would be expected, it's natural to look at the differences between the observed and expected counts. So we look at observed minus expected. Okay, that makes sense because we want to know how far away from what we would expect is happening in what we observe. These differences are actually residuals, so we know adding up all the differences will result in the sum of 0, and that's just not very helpful at all. So we'll handle the residuals as we did in regression by squaring them. To get an idea of the relative sizes of the differences, we will divide each squared difference by the expected count from that cell. So to get our chi-squared test statistic, and it is chi-squared, not chi-squared, it's chi-squared, it is going to be the sum of the differences of the observed counts minus the expected count squared divided by the expected count. The chi-square models are actually a family of distributions indexed by the degrees of freedom, much like the t-distribution. The number of degrees of freedom for a goodness of fit test, and this is going to be different for the other chi-square tests, but for goodness of fit is n minus 1, where n is the number of categories, not the number of individuals who were sampled. Okay, so that's going to be huge. If I ever write a textbook, we're going to call it k minus 1 or something like that, where k is the number of categories, just because it gets confusing with n being different things, but in this case, n is the number of categories. So one-sided or two-sided. The chi-square statistic is used only for testing hypotheses, not for constructing confidence intervals. If the observed counts don't match, the expected statistic will be large. You'll get a big old chi-squared value, and it can't be too small. So the chi-square test is always one-sided because you can't be too small. It's only on one side. You're only looking at if it's a large chi-square value. If the calculated statistic value is large enough, we'll reject the null hypothesis because, again, the area toward the tail will be really small if the chi-square value is really large. The mechanics may work like a one-sided test, and we do consider it a one-sided test, but the interpretation is really, in many ways, many-sided because there's a whole lot of ways a distribution can not fit a theoretical distribution, a proposed distribution. So there's many ways the null hypothesis can be wrong. There's no direction in the rejection of the null model. All we're going to know is that it doesn't fit. Alright, so the chi-square calculation, the first thing you want to do is find the expected values. Every model gives a hypothesized proportion for each cell. The expected value is the product of the total number of observations times this proportion. It is imperative that you know this because you're going to have to calculate expected values for chi-square goodness of fit. Then you want to compute the residuals. Once you have expected values for each cell, find the residuals observed minus expected, square the residuals, and then compute the components. So it's the square of the residuals divided by the expected count. Then you get the sum of all the components. You find the degrees of freedom. It's the number of cells minus 1, or number of categories minus 1. And then you're going to test the hypotheses. You're going to use your chi-square statistic to find the p-value. Your calculator is going to be very helpful in this. It's going to be very helpful in finding that chi-squared value in the first place. Remember, you'll always have a one-sided test because the test statistic cannot be too small. Large chi-square values means lots of deviation from the hypothesized model, so they will give small p-values, which will be evidence to reject your null and evidence that supports your alternative hypothesis. But I believe the model. Goodness of fit tests are likely to be performed by people who have a theory of what the proportions should be and who believe their theory to be true. Unfortunately, the only null hypothesis available for a goodness of fit test is that the theory is true. So all you can do is measure your evidence that it isn't true. As we know, the hypothesis testing procedure allows us to only reject or fail to reject the null. The best statement you can say about the actual distribution fitting is that the data are consistent with it fitting. We don't actually provide evidence for it, just just that the data are consistent with it. We can never confirm that a theory is in fact true. At best, we can point out only that the data are consistent with the proposed theory, just like I said. Remember, it's just like the idea of not guilty versus innocent. Okay, juries never declare somebody to be innocent no matter what their mama may say on the news. All the jury can do is say that somebody is not guilty. Okay, that the evidence has not been strong enough to reject their guilt, their innocence. Okay, the data are consistent with them being not guilty. Okay, let's look at an example. After getting trounced by your little brother in a children's game, you suspect that the die he gave you to roll may be unfair. To check, you roll it 60 times, recording the number of times each face appears. Do these results cast doubt on the die's fairness? Okay, so here's what we've got. Each face of the die, 1 through 6, just like a normal die. Let's see what happens. 1 comes up 11 times, 2 comes up 7 times, 3 comes up 9 times, 4 comes up 15, 5 comes up 12, and 6 comes up 6 times. If the die is fair, how many times would you expect each face to show? So we're figuring out the expected count. And in this case, all the expected counts are going to be the same because you expect the die to show up with each face, to roll each face an equal number of times. You expect a uniform distribution. If the die is fair, the probability of each face, 1, 2, 3, 4, 5, or 6, is going to be 1 out of 6. So we want to take that proportion and we want to multiply by the total number of rolls. So 1 6 times 60 and we get 10. So we would expect each face to have shown up 10 times. What kind of distribution would the outcomes follow if the die is fair? Well, since all 6 faces would have the same expected number of outcomes, 10, the distribution would be uniform. You would expect 10, 10, 10, 10, 10, 10. We're going to state our hypotheses. All right, the null is that the die is fair or a uniform distribution is a good fit for the outcome of all rolls of this die. Our alternative will be the die is unfair or a uniform distribution is not a good fit for the outcomes of all rolls of this die. We're going to check the conditions, and those are that our data are counted. They're summarized as counts, randomization, and expected counts at least being 5. The data is summarized as counts of outcomes for the roll of a die. Actually, it should be data are summarized. Sorry, little grammar error there. The outcomes of the roll of a die are random. That's the assumption for, rolling a die. And then the expected count for each face is 10, which makes them all greater than 5. How many degrees of freedom are there? Well, remember, it's the number of categories minus 1, so 6 minus 1 is 5. Okay, we're going to find the chi-square test statistic and the p-value. So to do this in your calculator, which I'm sure you want to do, open a new document. In a spreadsheet, make an observed list and an expected list. In the observed list, put the counts for each face, so what you actually see, so 11, 7, 9, 15, 12, 6. In the expected list, put the expected number, which is 10, for each face. Okay, from there you're going to select a menu, and we're going to do something very statistics oriented. So we're going to go to statistics. In fact, we're going to do a test. We want to do a chi-square goodness of fit test, so go to stat test and choose chi-square goodness of fit. Select observed from the observed list and expected for the expected list, and enter the degrees of freedom 5 for DG and select OK. Okay, so you should get chi-squared equals 5.6 with 5 degrees of freedom and a p-value of 0.3471. You really need to do this. If you did not actually get out your CAS and do this, you need to pause the video right now and actually do this to make sure that you can do a chi-square goodness of fit test with your calculator. Okay, part G is going to be to state our conclusion. Due to our large value, which rounds to be 0.35, we failed to reject our null hypothesis. There is no significant evidence that the die is unfair. Or you could say there is no significant evidence that the distribution of die faces is not uniform. Remember, you always report the p-value, state whether we're going to reject or fail to reject the null hypothesis, and then you state whether or not you have evidence for the alternative. So we fail to reject our null, so we do not have evidence, significant evidence for our alternative. All right, let's look at another example. In its study, When Men Murder Women, the Violence Policy Center reported that 1,857 women were murdered by men in 2005. Of these victims, a weapon could be identified for 1,752 of them. Of those for whom a weapon could be identified, 966 were killed by guns, 390 by knives or other cutting instruments, 136 by other weapons, and 260 by personal attack, battery, strangulation, etc. The FBI's Uniform Crime Report says that among all murders nationwide, the weapon use rates were as follows: guns 63.4%, knives 13.1%, other weapons 16.8%, and personal attack 6.7%. Is there evidence that violence against women involves different weapons than murders in general in the United States? Okay, so our null, anytime it says, is there evidence, and then blah, 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 that means you're going to do a test. So we know we're going to do a hypothesis test. We're looking at these observed counts of murders by various weapons against women, and we've got proportions here, or percentages, same difference, of what happens in some other distribution, and we want to know how well what we observed matches what we would expect under what was reported. So we want to do a chi-square goodness of fit test. So our null hypothesis states murders among women had the same distribution of weapons as murders in the United States, so that there's no difference between our observed, or no significant difference, and our observed distribution of weapons for women versus our expected distribution of weapons used against women. So our alternative is murders among women have a different distribution of weapons as all murders in the United States, so that that distribution is not a good fit. So let's check our conditions. The data are summarized as counts of murders. Each murder is plausibly independent of the others. We don't have any evidence that they're not independent of each other. The expected counts are at least 5, and the way you would check that is you would go through and do each percentage this time, because we're not saying that it's uniform. We're saying that 63.4% would be from guns, 13.1% would be from knives, and so on. So this is different than the die example, because in the die example you expect there to be a uniform distribution of outcomes. Here we don't. We expect the vast majority of the outcomes to be using guns as the weapon. Okay, so we do 0.634 times the 1,752 murders against women, and that equals 1,110.768. And then the 0.131 times 1,752 equals 229.512. 0.168 times 1,752 is equal to 294.336. And 0.067 times 1,752 equals 117.384. I will conduct a chi-square goodness of fit test, remember you need to identify the test that you're going to conduct either by name or by formula. So I did by name. Look at the last example for CAS instructions, and that will tell you exactly how to enter this into your CAS with the two lists. So I get chi-squared equals 389.54 with degrees of freedom of 3 and a p-value that rounds to be 0, which is tiny. So due to our small p-value, we reject the null hypothesis. There is significant evidence that murders among women have a different distribution of weapons as all murders in the U.S. So I report my p-value and I state whether I reject or fail to reject the null. And then in context of the problem, I say whether there is significant evidence for my alternative. This is where I'm going to get context, is in my second sentence. So small p-value means we reject the null, which means we do have evidence for our alternative. Okay, guys, that's it for chi-square goodness of fit. Next time we will talk about a couple of other chi-square tests. And thank you for taking good notes. Make sure you do the problems to try on your own, and I will see you in class.